So now we're going to explore section 5.6, which covers Hess's Law. And Hess's Law is really quite useful. Why? Well, because it allows us to calculate the delta H of basically any reaction, regardless of the complexity or difficulty associated with gathering said delta H value. The reason why it's so useful is because instead of measuring each and every reaction type that exists, which would lead to a huge category or huge library of delta H values for millions and millions of reactions, instead what it utilizes is the individual steps that occur within a reaction. We actually find those delta H values and then subsequently sum the values of those individual steps. So basically we take the delta H values from more easily calculable or measurable reactions and subsequently add up all those values to give us our overall reaction. So if we look at an example here below, notice that we are actually wanting to look at the equation that actually interrelates the combustion of methane to its corresponding products, but we want our corresponding products in the gaseous for the CO2 and liquid state for the H2O. Now, we might have the delta H value for products for that specific reaction in the gaseous state for CO2 as we desire, but in the gaseous state for H2O. With that being looked at, we notice that the reaction 1 up here is not the same as the reaction that we desire down here. So what we need to do is actually look at the interconversion between gaseous H2O and liquid H2O. And we can get this pretty easily experimentally, going from gas to liquid, so condensing some water vapor to its gaseous state. And we can get the delta H value associated with that. So what we can actually do is we can sum the two equations. If you notice, we bring down all of our reactants. Okay, they come down. Okay, and we sum all of our products. They come down. Okay. Once we've done that, we want to cancel out the things that repeat on each side. So notice we have two H2Os over here, two H2Os on the product side. Those cancel out, and we're actually left over with, we have remaining, our desired reactants and our products in their desired state. What you also need to notice is that we obtain our delta H value by summing the two values that we have here, which gives us an overall negative 890 kilojoule delta H value. Okay, so guys, as we mentioned in our previous lecture, the states of your products and reactants really matter, right? So the state of the matter matters. Okay, so we need to be paying attention to the subscripts that we see on our balanced equations. Or thermochemical equations. If they don't match up, okay, it's not the correct equation. So if what we saw here in terms of it being in the liquid state is not what we see up here, we definitely know that there's going to be an extra step in terms of the summation values. So make sure you're paying attention to that whenever you carry out Hess's Law reactions, or whenever you utilize Hess's Law to calculate delta H's for overall reactions. So let's actually look at a problem here. Okay, so a lot of times these kinds of reactions are given in this type of format. Okay, what they'll do is they'll give you a reaction and they'll ask you to determine the delta H, or the heat of the reaction, for this specific equation here based on a set of equations that they provide. Now, you need to make sure that the set of equations that you have here, okay, have the appropriate coefficient values as well as are on the correct side of the arrow. So there's some flipping, multiplication, and potentially division that needs to occur in order to get to the delta H value that we desire. So if we go ahead and we look at this problem, you can approach this in many ways. The way that I usually go about it is I first look at where the reactants or products are on each side of the arrow. So if we look at this first equation right here, okay, notice N2, H2, neither of those end up in the equation above. Okay, so because of that, those really aren't of importance. Okay, really what we need to be looking at is the location of the NH3. And if we look at the location of this NH3, we notice that we have it on the product side here, but the reality of it is in the equation above, we have it on the reactant side. So that should immediately tell you that you're going to need to flip this equation over. Okay? Additionally, you need to make sure, obviously, that you're paying attention to states of matter. Okay, in this case, you have gas. That's what you desire, so you're okay there. And lastly, you need to look at molar composition, right? So in this case, this delta H that we see here is in the context of 2 moles of NH3, but up above we have 4 moles of NH3. So as we flip the equation, we're also going to need to multiply it by 2. So as you see here, okay, we are going to reverse the first equation and we're going to multiply by 2. When we do that, okay, our NH3 now becomes a reactant. We have our products on the right-hand side. Okay, we're also going to multiply, so our coefficients all increase, okay, by a factor of 2. And the sign, because we flipped, of our delta H is now positive instead of negative, and it has been doubled because we multiplied the whole reaction through by 2. Okay, so you've done one of them. You now have your NH3 on the right side, on the correct side, so you can move on to the next thermochemical equation. So if we look at this one right here, okay, once again, same approach. You want to look at where reactants and products are. Okay, so it's nice. We have our N2 that has nothing to do with our equation in terms of our overall goal. Okay, so we can ignore that. O2 is definitely a reactant. Okay, so we're good with that being on that side. And NO is definitely a product, okay, on our overall chemical. So this equation is written in the right direction, or the correct direction. Okay, the things we need to look at are, once again, the states. Okay, they match up. And we also need to look, once again, at the coefficients. Okay, so we have 4 NOs up here, and we only have 2 down here. So we know that overall, we're going to multiply this equation by 2. When we do that, our coefficients change by a factor of 2, and our delta H value for this specific reaction increases by a multiple of 2. So, now that we've seen that, we should be able to easily apply these same rules or the same approach to the last equation. In this last equation, we're going to look at what we have as reactants and products. Okay, H2 we don't really care about. O2 we definitely need that on the left-hand side of the arrow in the equation above, so it's in the right position. Our H2O2 here, though, is also in the right on the right side of the equation. Okay, so everything's in its desired location. However, the coefficients, once again, are off. So in this case, we have a 6 in front of our H2O up in the desired equation that we're solving for, right? And we have a 2 down here on the equation that we were given. So what we're going to need to do in this case is multiply through by 3. Once again, all the coefficients, okay, they get multiplied through. Your delta H value gets tripled in this case, and then you can proceed to the next step. So the next thing that you're going to be doing is you're going to be summing these equations, right? So you flip them and multiply them through and set them all up so that everything, all the reactants and all the products should be on the correct sides, and that you have the correct molar amounts of each of your reactants. Okay, so once we sum all of these, right, we have all of our reactants, right? Okay, we have all of our products. Okay, these should all sum up appropriately like this. Okay, Once you've written out the reactants and the products on both sides of the arrows, okay, you're going to cancel out those things that are repetitive, right? So on the left side of the arrow, we have this N2. Okay, on the right side, we have N2, we cancel it out. On the left side, we have H2, okay, and H2, they cancel out. Okay, and we end up having our remaining reactants and products, okay, which represent our desired overall reaction that we were calculating for. At the same time that we're summing our reactants and products, we're also going to be summing all the delta H values that we calculated based on our equation flipping and multiplying. Okay, and this will give us our value down here. Okay, and a question that you might be asked after you've calculated something like this is this reaction endo or exothermic? Okay, well, under constant pressure, right, delta H is equal to Q, right? In this case, delta H is negative, okay, so Q is negative, and in that sense, the reaction is going to be exothermic because it releases heat. Additional practice is going to be found on page 181.